Okay, so you know that fluffy pink wool fiberglass insulation you probably have sitting up in your attic right now? Well, have you ever actually wondered how it's made? Or more importantly, have you ever stopped to think about what kind of invisible byproducts are created when factories are just churning that stuff out by the ton? Welcome to this explainer. Today we are going to unpack what is honestly a fascinating and highly rigorous scientific detective story. We're looking at a specific document from the Environmental Protection Agency, and it goes by the name Method 5E. Now I know, that sounds like a secret government protocol, and to be perfectly honest, it kind of reads like one. It's this official, incredibly complex process used to track down, capture, and measure microscopic pollutants that are literally hiding in the exhaust of wool fiberglass manufacturing plants. We're talking about a world of extreme heat, highly toxic chemistry, and some absolutely meticulous forensic accounting. So here is our investigative roadmap for today. We'll start with the invisible emission problem, then look at the tools of the trade, move on to catching the particulates, jump into analyzing the trap, and finally look at the final calculation. All right, part one, the invisible emission problem, unseen factory outputs. Okay, let's dive into this. Our primary target today is something known as particulate matter, or PM. You see, when factories manufacture that wool fiberglass insulation, the process naturally releases particulate matters straight into the exhaust gases. And the tricky thing is, this isn't necessarily that thick, billowing black smoke you can easily spot from a mile away. A lot of this stuff is totally elusive, completely invisible to the naked eye, and incredibly tricky to measure. And that is exactly where Method 5E comes in. You really have to think of this EPA document not just as some boring set of bureaucratic rules, but as the ultimate forensic investigation manual. Actually, scratch that, it's more like a highly precise playbook. It gives scientists the exact step-by-step instructions they need to pull out those exhaust gases, trap that invisible particulate matter, and actually weigh it with absolute certainty. Moving right along to part two, tools of the trade, hazardous chemistry. So how do you catch something you can't even see? Well, scientists have to bring in tools that are just as extreme as the industrial environments they're testing in. Right at the top, in section 5.0 of the method, the EPA lays out some incredibly serious safety warnings. We are dealing with hydrochloric acid, or HCl. And let me be clear, this isn't that mild stuff you might remember from high school chemistry class. These vapors are highly toxic. They're extremely irritating to your eyes, your skin, your nose, your lungs, and they can cause severe, permanent damage. It's kind of crazy when you think about it. Just to measure air pollution, the people running these tests basically have to suit up like they're about to defuse a chemical weapon. To put that level of danger into perspective, just look at this number. If you were exposed to a concentration of just 0.13 to 0.2% of hydrochloric acid vapor in the air, that can literally be lethal in minutes. Not hours, minutes. No way, right? It's just a really stark reminder that protecting our air quality and doing this environmental testing often forces scientists to get up close and personal with some incredibly volatile substances. And the thing is, HCl isn't even the only dangerous chemical in play here. The other major tool they use is sodium hydroxide, or NaOH. As we're going to see in just a second, this chemical is absolutely vital because it acts as a liquid trap for those exhaust gases. But handling it comes with some severe risks of its own. It causes major tissue damage to the skin and eyes, and it reacts exothermically, meaning it releases a ton of heat when it touches even limited amounts of water. The stakes for setting all this equipment up are incredibly high, and that's before they've even collected a single sample. Which brings us to part three, catching the particulates, setting the trap. Okay, so the crucial thing to understand here is that particulate matter inside that hot factory smokestack exists in two different forms. You have solid particles and you have vapors that will eventually condense. To make sure they catch both, Method 5E utilizes this brilliant two-part trap. First, they extract the gas using what's called an isokinetic probe. Basically, that just means they pull the gas out at the exact same speed it's already traveling up the smokestack, which ensures they don't accidentally skew the sample. Now the gas immediately hits a heated glass fiber filter, which is kept at a scorching 120 degrees Celsius. This acts like a physical net to catch all that solid mass. But what about the sneaky vapors that manage to slip right through that net? That's where part two kicks in. The gas flows directly into impingers, which are essentially specialized glass vials, and these are filled with that super hazardous 0.1 normal sodium hydroxide we just talked about. This liquid acts like a chemical sponge, rapidly cooling and catching those condensed gases. Now, once the test is actually finished, you can't just unhook the machine, throw it in the truck, and drive back to the lab. Oh no. Every single microscopic particle has to be meticulously accounted for. The scientists divide their total catch into 5 very specific containers.
Container 1 holds that heated glass filter, which is carefully dried. Containers 2 and 3 hold water and acetone rinses of the probe itself. Yes, they literally wash the equipment down to make sure not a single speck of dust is left clinging to the glass walls. Container 4 holds silica gel, which is used to capture any lingering moisture. And finally, Container 5 holds that absolutely crucial sodium hydroxide liquid from the impingers. Every single piece of evidence is completely locked down.
Let's head into the lab for part 4, analyzing the trap, the interrogation. Back in the laboratory setting, dealing with a solid filter is actually pretty straightforward. You just weigh it. But Container 5? That liquid trap is a real chemical mess. The scientists are hunting for something specific, total organic carbon, or TOC. The problem is that sodium hydroxide liquid usually contains a massive amount of inorganic carbon that totally throws off the readings. So they have to aggressively pre-treat this sample to basically strip the disguise off our target. First, they blast it with a blender or ultrasonic waves to homogenize the whole thing. Then, they introduce that highly toxic concentrated hydrochloric acid to force the pH down to 2 or less. Finally, they warm the whole mixture at 50 degrees Celsius for 15 minutes. This is a harsh, aggressive chemical interrogation, and it forces those interfering inorganic materials to break down completely so the true organic carbon can finally be measured. Now, what's really interesting about this next step is how they actually measure the carbon. They split the sample in half and run it through 2 completely different furnace channels using a nondispersive infrared analyzer. On one side, the total carbon channel uses a blistering 950 degrees Celsius furnace to just completely burn everything, organic and inorganic alike, turning all of the carbon into CO2. But on the other side, the inorganic carbon channel uses a much cooler 150-degree furnace mixed with phosphoric acid. And this is a really clever trick because it only liberates CO2 from the inorganic carbonates, leaving the organics totally untouched. By taking the results from that high-temp total destruction and comparing them against the low-temp selective liberation, they can mathematically isolate the exact amount of total organic carbon in the sample. It is just such an elegant, multi-layered solution to a really complex chemical problem. And that brings us to part 5, the final calculation, the verdict. Because at the end of the day, all of that dangerous fieldwork and that meticulous lab chemistry ultimately boils down to hard mathematics. The scientists take the peak heights registered by the infrared analyzer and they map them directly to standard calibration curves. This generates specific variables, things like the mass of the condensed TOC collected in the impingers and the concentration of condensed TOC in the liquid sample. These mathematical variables represent those elusive, invisible gases that were successfully trapped, quantified, and ultimately converted into undeniable, rock-solid data points. And it all culminates in this ultimate formula. The total particulate concentration is really just the sum of 2 distinct journeys. It's the solid mass that was caught like a fish in the physical net of our heated glass fiber filter, plus the invisible condensed particulate matter that was chemically trapped in the sodium hydroxide sponge, blasted with acid, and burned in a furnace. Only by combining both the physical solids and the condensed organics can the EPA get an accurate, legally binding measurement of what is truly coming out of that factory stack. Which leaves us with this final thought. Method 5E is such a perfect example of the invisible scientific rigor that completely surrounds our everyday lives. So the next time you see a roll of that standard pink wool fiberglass insulation at the local hardware store, or maybe you're unrolling it in your very own attic, ask yourself, how much hidden chemistry, hazardous fieldwork, and intense mathematical deduction was required just to ensure that the air stayed clean while it was being made? Thank you so much for joining me for this explainer. I really hope it gave you a brand new appreciation for the unseen science that is constantly working to protect our environment. Catch you next time.